All right. So I guess last time we left off, like there was this strain tensor. We introduced the strain tensor, right? So yeah, obviously the strain tensor was epsilon ij is equals to half of gradient of the displacement tensor field, and plus the gradient of displacement tensor field and its transpose. So like that was the symmetric part of the gradient displacement tensor field. And so similarly, there's also this rotational tensor that is like the antisymmetric part of the gradient tensor field. And like this rotational tensor would obviously have three components since it is antisymmetric. So the diagonals would be zero, and there would be three components along the nine non-diagonal elements. So like so obviously the dual, like I mean obviously as for any antisymmetric matrix, we said that there would be like a tensor associated with itself. Like this is this the rotational tensor associated with. So like I mean if we have the matrix component that is like theta 2 3 or like theta 1 3, and like then basically we can have this thing, like the basically the dual vectors for that. So like basically the rotational, this is the like the dual vector for the rotational tensor, antisymmetric tensor. So it's like basically it's simple as the same, like it's the antisymmetric part of this. So you can basically find the tensor, and then from the tensor you can find this dual vector, which is basically the rotational vector. So like it shows you which direction your body is basically rotating in. So now basically we can obviously discuss on some different types of extension, like one of them being the simple extension, where wherein like our displacement field is like C1x. So like obviously you can basically now given any displacement field, you can like easily find the epsilon, like the gradient of it, the epsilon strain vector. So basically in this case also the like the gradient matrix is like very simple. It is like gradient of u is equal to c1, and then it is for some reason like it's c1, and like you can also find this epsilon tensor, and you can also find this and like I mean there's also this other like tensors, like the rotational tensor, and there's also this like f tensor, like I mean which we discussed, this is grad u plus 1. So like that would be 1 plus c1 and 0 0 and 1. So yeah. So basically, this is simple extension, and there are other cases such as this is like the normal extension, like in which there is this C1x and like C2y. So basically, it just basically strain is in x direction too, and strain is in y direction too. Note that there is no shear stress in this case, so like it's already diagonalized. So like this epsilon strain tensor is like basically diagonal matrix, and it's not there are no shear strain components. So like epsilon xy component is zero, and there's also no rotation. So like the theta is zero as such for that case too. And like for shear stress, our like the u component of the field is like c1 y, and like the by convention, so like it's c1 y, and hence like we would have these we can like basically again take the derivatives, and like we can find the gradient tensor field. And like once we have the gradient tensor field, its symmetric part is the strain tensor field, and its anti-symmetric part is like the theta, the rotation, the local rotation. So like yeah, in this case also we have a local rotation, and in this case also we have like it's a pure shears, like it's a pure shear stress. So there's no epsilon x or epsilon y components. It's just basically the two components on the like side, the c1 by 2 and the c1 by 2 components. Yes. So basically, there are also the shear rotation, and there is also the shear without rotation. So like the shear without rotation is an important case. It's like in that case there is just shear, that there's just pure shear, and there is no actual rotation as such. So the rotation tensor is like zero, as you can see in this case. The rotation tensor is basically zero. So basically, with this, like these are the like four basic kind of shear strains which one might encounter, and like I mean, we for simplicity purposes, we basically model them like this. And so in the next basically our next topic is strain in any arbitrary direction. So like if I set up a new basis, like that is e1 dash and e2 dash, so what exactly would be the strain in that direction, right? So obviously now we know that strain is a tensor, right? So if I have a new basis, and that new basis is orthogonal, so basically we know that there's this formula for like I mean we can there's this derivation too which I have written, which is the formal derivation. But like I mean if we also like think about it, we can basically, this is like the formal derivation for each and every component. Like we have this epsilon theta component, and we have this gamma theta component, But like, I mean, we know that epsilon is a tensor, right? So like, instead of going through all the first, we know that epsilon is a tensor, and we can basically just transform it into the new coordinate. So like, I can take write the epsilon dash in the new coordinate, the strain in that new coordinate direction, and basically I can just basically write the transformation matrix from the original coordinates to the converted coordinates. So epsilon dash is equals to q transpose epsilon times q, which is like basically how we defined it. And in matrix format, as we know that for matrix, if we write in matrix format, we have to take the transpose of it for each and every vector. So like, basically that is, since epsilon is a symmetric vector, epsilon transpose is also the same. So basically it's just the same. So it's just basically the convention. There's nothing a lot difficult concept going on here. It's just basically we are basically transforming the epsilon tensor into some other coordinate basis, and in that coordinate basis, that epsilon tensor would basically give us the strain in those two directions, which are the principal directions for that. And so yes, I mean, this is our transformation is easy and useful. Like, I mean, this is how we basically get eigenvalues and eigenvectors and max and min state. So basically next topic is basically that. So maximum and minimum state. So like, I mean, after like basically writing this matrix we have in 2D. So after solving, basically we know that we have this formula for like the shear strain. Like, if I take at any angle theta, I guess the screen is stuck here, but I'll just, so I have this angle. So like, for any epsilon theta, I have this formula for like the strain in that direction if I take it an angle theta. So basically, if I simplify this, I can use this like cos square theta. I can use 1 plus cos 2 theta by 2, and basically in the end I would basically get this formula. And like, if I have where to differentiate it for maximum state, obviously I would need maximum state. So I would differentiate it, and I would get this condition, that is tan theta is equals to 2 epsilon xy upon epsilon x minus epsilon y. So basically at this angle, I would have either the maximum strain or the minimum strain. So basically, if we consider that epsilon xy is greater than 0, and epsilon x minus epsilon y is also greater than 0, all positive. So in that case, we like, in that case we observe that there's this thing that the the second derivative is basically 0 when we take a theta equals to theta naught from 0 to pi by 2. That is, if I take a theta equals to theta naught from 0 to pi by 2, we have a maximum strain value. So if my epsilon xy and epsilon x minus epsilon y is positive, then from 0 to pi by 2, I will have a theta in which, like, at theta equals to theta naught, at which this equation satisfies. At that point, I would have a like a maximum strain value. So I'll try to annotate here. Yeah. So basically at sin theta equals to sin 2 theta equals to 0. So like, at basically theta equals to theta naught, I would have like a maximum value, and like at some at other coordinate, I would have a minimum value basically. As so, like, if I were to represent it graphically, so here is like basically, there is like basically epsilon x, and there's this epsilon y, and there's this maximum at a point at epsilon theta, and there's also in a perpendicular direction to epsilon theta, there's also a minimum in that point. So like, we basically kind of denote this direction in which there's a maximum like strain as the principal direction. So there are quite nice properties for this. Like, let's just look at the values. So like, after substituting it, we get this maximum value of theta as half of epsilon x plus epsilon y plus times epsilon x minus epsilon y whole square up plus epsilon xy whole square. Yeah. So basically, this is the current like maximum and like minimum value. So it's like basically, as you can see, it's a like differential, like not it's like a quadratic formula. So this is like the formula for max and minimum strain, and like we know the angles too. Like, we have calculated the angles for this case too. Now, basically, what we can also observe is that this gamma of theta, like the shear strain which we consider, in that case, both the shear strains are 0, like in the minimum and maximum. Like, at the thetas which we consider, in which shear strain is maximum and minimum, like the actual strain on maximum and minimum, the shear strain is 0 in that case. So like, at theta max, gamma is equal to 0, and at theta min also gamma equals to 0, which implies that epsilon xy and epsilon yx both are 0. at that angle theta. So what one can also like observe is that this is it. What, yes, exactly, what one can observe is that I can like if I were to basically write my epsilon matrix right here, so epsilon would be epsilon max, epsilon min, this is 0 and this is 0. So basically epsilon has transformed, like in the other coordinates epsilon has transformed into a diagonal matrix. And like obviously as we have seen in ME 106 that this is basically the eigenvectors, like I mean the directions are eigenvectors of the strain matrix. And this is basically the eigenvalues, the epsilon max and epsilon min are basically the eigenvalues of the strain matrix. So like there are like I mean as you can see that at eigen, like if I take the eigenvectors of a strain matrix, like if I have the strain tensor, then if I take its eigenvalues, then if I take them as a basis, then when I transform it to those like basis, the eigenvalues as the basis, then in that case I would have a diagonalized matrix, like I would have a diagonal matrix with eigenvalues as its diagonal elements, like lambda 1, lambda 2, and lambda 3 as its eigenvalues would be its eigenvalues. So basically it's the same as that. So basically the eigenvectors are the directions at which the shear strain is maximum and like the shear strain is minimum, like those are the two values at which the shear strain is maximum and minimum in the eigenvectors, in the eigenvector directions basically. So now basically and also for like maximum engineering strain we can like basically also find the maximum for engineering shear strain by like differentiating it. And you can basically observe that, and for that maximum we have basically it's perpendicular, like it's minus 1 by slope of, like I mean that kind of thing, minus 1 by m and minus 1 by m. So it's basically at a 90 degree, the 2 phi angle is basically at 90 degree with the 2 theta angle. So what we can do is basically we can just look at this, like I mean we have this we like have differentiated this. So basically we have this condition like tan 2 phi is equals to minus epsilon, so like we, this is the condition. And like again like just doing all the calculation over again, and we have, so basically in the end we have this two directions again. So this is phi 1, phi is the direction in which shear strain is maximum, and theta is the direction in which the normal strains are maximum and minimum. So basically theta 1 is the direction where normal strain was maximum, right? So like theta 1 minus pi by 4, that angle I would denote as phi 1, and at that angle phi 1 my engineering shear strain or gamma xy would be maximum. So like the gamma xy would be maximum at angle phi 1, and gamma xy would be minimum at angle phi 2, which is corresponding to theta 2. Theta 2 was the direction where like the strain was minimum, and we basically subtract pi by 4 for like 45 degrees from both of them. And like this is basically the graphical representation, like if this was theta 1, then phi 1 is 45 degree minus theta 1, and if this is theta 2, then phi 2 is basically 45 degree minus this theta. So basically it's just the angles which you have to remember, like I mean it's very simple, you can basically remember them, and it's like very simple to also calculate and check them. So now that basically we have this, like it's all like you can also have a look at the values right here. So yeah, these are the values at, like I mean at like phi 1, what are the basically strain values. We know that at phi 1 the shear strain would be maximum, right? So like the maximum value of shear strain is like given here, and the minimum value is also given here. Minimum value is basically the negative of that, so that's why it's minimum. And all these are like basically the values at 45 degrees. And there's, and also to note that there's the engineering strain, like the normal strain is not non-zero for this case. Like I mean when we had the maximum normal strain, at that case the shear stress was 0, but in case of maximum shear stress the normal strain are not zero, non-zero, so they are also having some value at both of this angle phi 1 and phi 2, and like they are having the same value basically. But on both angles we have, at one angle we have a maximum shear strain, and at another angle we have a minimum shear strain. So basically these are the like powerful results which we basically consider. And like as I said, this is like basically an eigen, this can also be converted into an eigenvalue problem. So like if I find the eigenvectors of the strain matrix, then basically those eigenvectors would be the direction at which I have the maximum strain, and in those direction I will have the strain vector, I mean the strain tensor as diagonalized. I mean the strain tensor would be lambda 1, lambda 2, and lambda 3. Like I mean those would be the diagonal elements of the strain matrix, the strain tensor. So yes, it's basically the same as, like I mean, we just basically going through all that. So another thing to note is that the eigenvalue which we found by eigenvalues of the strain tensor is basically the same as the maximum and minimum stress which we found during that. So basically, as we said, that the eigenvalues are basically the diagonal elements. So like obviously they are the diagonal elements of the strain tensor too, and hence the eigenvalues are basically the maximum and minimum values of strain respectively, the normal strain respectively. So yes, as you can see, this is like the eigenvalues which we calculated. So yeah, I guess it's quite simple. So like I mean, keep that in mind. I mean, it's like not very mathematically intense, but it's also very simple and intuitive to understand that if you have the eigenvectors, then you can basically easily get that, get all the values and etc. and stuff like that. Get the maximum maximum normal strain, and like the zero shear stress and all that. Zero shear stress. Now the last topic for like the before midsem is like the strain compatibility. So basically we know that like if we know the displacement vector field u, v and w, then basically it's very easy to calculate the strain tensor, right? But now let's suppose that we are given six strain components. Like I'm given the functions for each epsilon xx, epsilon yx, and all the components of strain. So since it's a symmetric matrix, it would have six components, right? So if I'm given this six component for strain, and suppose like I have to find the displacement vector field. So displacement vector fields are total three fields, right? So those are three variables, and we have currently six equations at in our hand. So basically there might be a chance that we might get more than one solution for these equations. And like if we get more than one solution, then there might be a problem. Like let's suppose if I take a triangle ABC, then at point B, like if I consider AB, then AB vector field A, like the displacement field according to displacement field A, it would go to A1 dash. But if I considered CA point, then according to displacement to field 2, it would go to A2 dash, right? So in that case, A1 dash, like the point A is basically getting mapped to two different points from the displacement vector field. So that is basically not possible, right? So like if we are given the strain tensor, then we would require some more little additional information for the displacement vector field too. If we are given the strain like to calculate the displacement vector field, and for it to be single values, there are some additional conditions which are to be imposed on the on the strain tensor. So like I mean the strain tensor function, so that we would those that would mean that we would have a basically we would have a single value displacement field. Like I mean this is the displacement field which we have currently have. It does not have a like I mean it has two values for one point, a point. For a point it has two values, so we want it to be single value. So some additional constraint must be imposed on the strain tensor. So basically after like some like calculations, we can like basically this is like the calculations which you can just basically go through the notes. And like I mean after the finally after like everything after like calculating everything, we basically find that this is the compatibility equation. And like this is the compatibility equation, that del square of epsilon x, the x component and its derivative with respect to y twice, and the y component and its derivative partial derivative with respect to x twice is equals to twice of the epsilon xy times del y del x. So like basically this is the equation for 2D. And like if my strain epsilon x and epsilon y and epsilon xy satisfy this relation, that means that the vector field which I would get from the solving these epsilon x, epsilon y, and epsilon xy would obviously be single valued. It would not be ambiguous, or it would not have more than one value. So basically, these are the conditions which the strain vector field has to satisfy it if it like originates from a actual displacement vector field. So yes, basically these are the like compatibility equation for strain. So this was for the one in 2D. So basically in general for 3D, this the above equation is valid for in general 3D. and from like after evaluating, like I mean writing this out, and like after a lot of bookkeeping, we would get like this six equations. So like as I said, this first one is like the basically the same one as we discussed in 2D. So the same thing for YZ and same thing for XZ we would write. And there's just also three another set of equations which are like as follows right here. Yeah, I'll just basically zoom in so that you can have a better look at it. And like basically you have to repeat the same thing for Y, and you have to basically repeat the same thing from Z. They are basically like very simple, like they're not simple, but they are basically very easy to remember. Like once you remember these two equations, you can just basically convert them from XY to YZ, from XY to XZ, and so on. So basically, if you are given a strain tensor, then these six equations the strain tensor must satisfy. Then only you can guarantee that the vector field U will have a single valued solution. So there are two proofs. One of the proofs requires Stokes theorem, and it's a quite advanced proof, which we would not be doing in this course as such. So in the end, I guess this is the strain compatibility thing. And lastly, there is this one topic of strain in polar coordinates. So if I have, obviously I know that there is this polar coordinates kind of thing. So basically we want to find strain in polar coordinates, right? So like if you want to find strain in polar coordinates, we first need to find out the gradient. What's the like gradient of a vector field in polar coordinates? So basically, here's the formula for like the gradient of vector field in polar coordinates. That is the grad u is equals to, these are the four components. Like I've written them as like 1 1 2 1 and like so on. So basically 1 1 2 1 1 2 and 2 2. So basically these are the four coordinates of the like matrix representation of gradient of displacement vector. So basically, for any given like displacement function u of r and u of theta, you can basically easily calculate this function. This is like the displacement gradient function. And like once you have this displacement gradient function, you can basically easily calculate the strain as like half of symmetric part of this and half of symmetric part of this. So like its derivation is not quite important as such, but you can basically remember the formula of what the like what are the functions and how basically we are taking the derivative for like I mean polar coordinates, like the polar coordinates r theta coordinates, and like how does basically the displacement gradient function look for this. Like if you have a function u of r and u of theta, u of r cap plus u of theta cap, you can basically find this displacement gradient function, and you can basically find the strain in r direction and theta direction by just by taking the symmetric part of this. And like I mean those formulas are also given for that. And like it's the same, basically you're just basically taking the symmetric and the anti-symmetric part of this. And I guess that's it. So basically these are the polar coordinates. So basically in the end I would just say that this course is basically quite mathematically intensive, but in the end like it's also something that you might understand if you try and put your intuition, like I mean think about it. It seems quite intuitive, but only if you think about it. But even if you don't understand it, there's no problem as such. You can just basically like learn these formulas and basically apply them in like all the, if you are given a field or something, you can just basically apply the formula and do the math and get the answer. It's as simple as that. So basically there's no loss as such in learning the formula. So you can just basically skip the derivation and you can just basically directly remember the final result, and you should know also how to apply those final results in there. And like so with that I guess that ends the syllabus till the strain. And I guess we would start with stress in the next half semester with that. And I guess this was it for this course for this half semester. Good luck for the exams. Thank you and bye.